Euler was a great mathematician born in the early 1700s, and one of the things that he worked with is what's now known as Euler's phi function, and that's the Greek symbol phi. And the idea is that we see, the way it works is we take a number like 10. And if I list out the numbers from 1 to 9, sort of everything less than 10, some of these numbers share a common factor with 10. For instance, 4 shares a 2 with 10, 5, 6 has a 2, 8. And some numbers have no common factor with 10. Those are known as being relatively prime to 10. 1, 3, 7, and 9. So there are 4 numbers less than 10 that are relatively prime to 10. So we say that phi of 10 is equal to 4. For another number, if I want to know, hey, what's phi of 12, for example, I could list out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Start crossing out. This has a 2 in it, this has a 2 in it, this has a 2 and a 3 in it, this has a 2 in it, this has a 3 in it, this has a 2 in it. Not much left. 11, 7, 5, 3, 1. There are 1, 2, oops, that 3 is actually not there either. So there are only 4 left. Now the answer is not always 4. Phi of 7, for example, 1, 2, 3, 4, 5, 6. Nothing gets crossed out. Nothing shares a common factor with 7. So the answer is 6. So the bigger the number is doesn't necessarily mean the phi of that number is bigger. Now there's a couple of cases. For instance, phi of a prime number. Remember, phi of 7 was 6. Well, and phi of 13 is going to be 12. And in general, it's always going to be 1 less, because all the numbers less than the prime are relatively prime to it. So phi of any prime is p minus 1. So if I say, what's phi of 89, and I tell you that 89 is prime, if you're not sure, it's going to be 89 minus 1, which is 88. A second case, something like phi of prime squared, like phi of 9 or phi of 5 squared. For 9, I could actually list out 3, 4, 5, 6, 7, 8. I'm even going to write the 9 there. And I can cross off the 3 and the 6 and the 9. And all that's left is 6 things. For 25, 4, 5, 6, 7, 8, 9, I'm actually going to write out all 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I'm even going to write the 25 there. Look what happens. I cross out all, the only thing that goes into 25 is 5, so I just cross out all the multiples of 5, 5, 10, 15, 20, 25. There were 5 of them. So I'm going to write that it was 25 numbers originally. I took away 5 of them, ended up with 20. Well, this 6 was 6 minus, there were 3. This might give you a clue as to say, well, phi of 7 squared, maybe that's just all the numbers minus the 7 multiples of 7. And it is. It gives us a general rule. Phi of prime squared is p squared minus p, which you could even write as p times p minus 1 if you want. Now there's a third case that's real important for cryptography, which is what if my number is not a prime and it's not a square of a prime, but it's the product of 2 primes. 3 times 5, I'll write that. Look what happens if I list out all the numbers from 1 to 15. First I cross off all the multiples of 3, and there are 1, 2, 3, 4, 5 of them. So there were 15 numbers. I subtracted 5 of them, all the multiples of 3. Now I'm going to subtract the multiples of 5. There's 1, 2, 3 of them. But look at this. If I count up the numbers that remain, there's 1, 2, 3, 4, 5, 6, 7. There's 8 of them, but 15 minus 5 minus 3 is just 7. I need to add back 1 because I subtracted this away twice. And I get my answer, which is 7. And this works in general. So for instance, 35 is 5 times 7. It's going to be 35 minus 5 minus 7 plus 1. 35 minus 5 is 30, 23 is 24, which is the right answer. I can change this into a formula. PQ. It's PQ minus P minus Q plus 1. Now there's something sneaky that there's something that's equal to this. It's P minus 1 times Q minus 1. Take a look. If I multiply these out using FOIL, I get PQ minus P minus Q plus 1. So the really easy way of doing this is just subtract 1 from each of the factors and multiply the numbers together. So now if I say what's phi of 55 or what's phi of 5 times 11, they're both primes. It's just going to be 5 times 1 times 11 minus 1 equals 40. Very useful formula. In case you're wondering how someone figured out the equivalence of those two things, there's something called factor by grouping. We factor a p out of the first two terms and a negative 1 out of the second two terms. Since these match up, I could factor that out. And those are some formulas for Euler's phi function. We only have 3 cases that we can do it for. The shortcut, p squared, that's p minus 1, that's p squared minus p, and finally pq is p minus 1 and q minus 1.